All right, so let's do another example of induction. This time I'm going to prove a claim about divisibility. So here the claim is that 2 divides n squared plus n, whenever n is a positive integer. So in other words, n squared plus n, whatever you pick for n, is going to be a even number, right? Or you can write it as 2 times some other integer. All right, so we're going to prove this by mathematical induction. Probably not the only way to prove this, right? I'm sure we could come up with another way. Maybe we could break it into cases. What if n is even? What if n is odd? I'll bet you can do it that way. But we're going to do it with induction. So our proof will begin with a base case. It claims that it's true for all positive integers. So we'll start with n equals 1. Say let n equal 1. Then I guess then we'll look at this number. N squared plus n will equal 1 squared plus 1, which is 2. Well, 2 divides 2, doesn't it? Every number divides itself. 2 divides 2, so the claim is true. At least for n equals 1. All right, now that's the only base case we need, right? We just need one case. Remember, so we've hit the first domino. We've touched the first domino. And now we're going to prove that that domino is going to knock over the next domino, and the next domino is going to knock over the next domino after that, and so on. And to prove that, we are going to do our inductive step. We're going to do it without assuming what n equals. We're just going to assume, we're going to say, assume this is true for n, and we're going to prove it's true for n plus 1. So our inductive step will begin with assume that 2 divides the number n squared plus n for some n. Positive integer n, right? Okay, now what we want to do is we want to examine n when replace what happens when we replace n with n plus 1. So we're going to look at the n squared plus n, except instead of n, it's now going to be n plus 1. So we have n plus 1 quantity squared plus the quantity n plus 1. All right, what does that look like? Time to do a little bit of algebra, right? Remember, we want to show that basically that this is a multiple of 2. And we are probably going to want to use that piece of information right there. So let's do a little bit of algebra. I'm going to do, I'm going to expand the first binomial squared. So that's going to be n squared plus 2n plus 1. And then we have plus n plus 1. And I don't need those parentheses on the second part. Now I'm going to do a bit of rearranging. So I have, if I combine all my like terms, I have n squared plus 3n plus 2, right? Now, not all of those are going to be even numbers necessarily. N squared, if n was an odd number, then n might be, n squared would be odd. We got 3 times n in the middle there. That's not so good. 3n may not be a multiple of 2. But what I've done actually isn't quite what I want to do, because what we had assumed is that 2 divides n squared plus n, right? So what I want to do is actually find n squared plus n embedded somehow in our n plus 1 case, right? So actually, I combine terms here into 3n, but I'm going to separate that back out into 2 parts. I'm actually going to write that as n squared plus n. And I'll put that in parentheses, just sort of like, set it apart. And then plus 2n plus 2, right? If I break the n cubed, sorry, not n cubed. If I break the 3n into n plus 2n, right, like that, then I can actually do some interesting stuff here. So by our assumption, that 2 divides n squared plus n, n squared plus n must equal 2 times k for some k, an integer. That's what it means to divide, right? 2 divides that means it's equal to a multiple, an integer multiple. So now I can write, going back to my equation here, I can write 2k plus, and then I can factor out a 2 here. Well, I won't do that just yet. 2k plus 2n plus 2. And then that equals 2 times k plus n plus 1. Now I'm almost there. Run out of space, so I'll move over to this side. What was I trying to prove? That 2 divides n squared plus n? Well, I just showed that, in fact, that when you do it for n plus 1 squared plus n plus 1, that is a multiple of 2. So I've actually just showed, therefore, 2 divides n plus 1 squared plus n plus 1. All in parentheses there. So I have completed, put parenthetically here, the inductive step is complete. Because I just showed, or we like to use the word, we like to talk about what we have done together. Because you and I are on this journey together. That's how you should think about it when you're proving something. You're taking the reader on a journey. We have now proven that if there was a P of n, I guess back here, P of n is the statement that 2 divides n squared plus n, right? That's the claim about n. We have proven that P of n, P of n implies P of n plus 1, right? That was the goal of the inductive step. So now, since we've shown that P of 1 is true, we've shown that 2 divides 1 squared plus 1. And we've shown that if 2 divides n squared plus n, 2 divides n plus 1 squared plus n plus 1. Now we can say, thus by induction, all of the dominoes will fall down, right? Push the first domino in the base case, and we showed in the inductive step that will not go to the next domino, and that will go to the next domino, so on and so on and so on forever. So now we've shown 2 divides n squared plus n for all n sequence. That's it.